Now that we kind of understand how the GLM is functioning at a basic level, let's go a bit further and plot this model so that we can even better understand what it's doing. I want to pull up the plot that I made before of our data. Let's run that again and run the bad linear model that we've got. With a linear model, right, you can use this handy AB line function and just plug in the model object, and it plots your model fit. Unfortunately, that's not quite so easy with the GLM. We're going to need to do a bit more, and we're going to use that predict function that we used to get confidence intervals on our regular linear model fit. And so to use the predict function, right, if you pull up the help page for predict, you'll see that predict, we're going to predict a string of values called pred_y in this case. The predict function takes your model object, TPB mod, our GLM here, and then it takes this new data argument, all right? That means that what we need to do is create that new data argument. So let's create an object first before we use the predict function called new x, because remember that this is a sequence of values across your x-axis that you're going to use to predict the values of your model fit. And so you don't want it to actually be just your data points, because then it would be restricted to just your data points. If you've got a point at 2 and a point at 8, there will be nothing in between. And so it'll just connect those two lines. So we want a continuous string of values across the complete range that we're trying to predict. And remember that this new data object has to be a data frame for the predict function to work, and it has to be a labeled one. So we have to say crural, because that's what in our model object, whenever we defined that GLM up above, crural is on the x-axis. It's the predictor variable, so we need to make sure that that's called the same thing in this new data object that we're making. So we want a sequence. In reality, our crural index really is between 0 and 1, but let's extend it because we want to plot on this huge scale to see the difference with our linear model. Let's say sequence from 0 to 10, and use the length out argument set to 100 to say that we want 100 different points between 0 and 10, evenly spaced points between 0 and 10. So now let's define that new.x object, and we're going to plug that into our predict function. So we're going to use the predict function to say predict values based on TPB mod for new.x. But we need to add another argument to the predict function. We need to say type equals response. All right. What this is referring to is the fact that we could predict values of TPB mod on the link scale, because remember that our GLM has a link function, which in this case is a logarithm. If we were to just run the predict function, it would predict values on our y-axis that were logged values, because the model is using a log transformation. So we don't want that. That would be type equals link. We want type equals response, which is saying, don't give me predicted values on the link scale, give me predicted values on the response scale, the response being our response variable, LTPB. Crural is the predictor variable, LTPB is the response variable. And I don't want logged values to be returned. I want actual real-world values of LTPB returned. So I need to say type equals response. If I run that, right, now we've got this pred_y object, which contains our predicted values for y, for LTPB, across all of that range of crural, that crural variable that we used to predict it. Now let's add this to the plot that we've got. Let's use the lines function because we've already got the plot made, and we're just going to add a line to it. So pred_y as a function of new.x, and remember to put $crural because it's a data frame. And let's plot this one in blue so we can see the difference. Now watch what this looks like, right? This GLM model fit looks like the regular LM model fit at kind of the values of our data. But if we extend out to the point where we start getting close to 0, which is the horizontal point right here where my cursor is, that blue line never goes below 0. This is because, right, when you take logarithms, you're able to account for the fact that our data are bounded by 0. That's what this log link function is doing. And so while our red LM fit here just continues into negative direction, predicting unrealistic values of a tibial breadth measurement, our blue model, our GLM fit, where we know that we can't have negative values, and so we used a log link function, it'll never predict those unrealistic values. Right? This is a big reason why GLMs are preferable in many cases. It can make for a much more realistic model. Now, as I said, if you were to zoom in all the way up here, we'll do that in a second, but if you zoom in all the way up here, you'll see that they're very similar models. There's hardly any difference at the range of Quirrell index that we really care about. So you could get away with using an LM function. You could. People would do that. But if you're dealing with data that's a little bit closer to 0, perhaps, you might want to think more about your model and what it's doing to predict realistic or unrealistic values. Now, of course, as I've said before, we don't want to just stop at plotting the model fit. We need to plot some sort of visualization, not just of the deterministic part of our model, but of the stochastic part of our model. We need confidence intervals. Now, in the case of an LM, right, all we would do is take this pred y object that we made, right, and take our kind of standard error, which we can get out of the predict function, and subtract that standard error multiplied by 1.96. Right? You'll remember that 1.96 is the number of standard deviations away from the mean that represents the 95% confidence intervals, negative 1.96 and positive 1.96. So when we take our standard error from the predict function, multiply it by 1.96, and either add it to pred y or subtract it from pred y, that gives us either the upper or lower 95% confidence intervals, respectively. But there's a problem. We're working with data that are log transformed, right? We've got this link function in our GLM. That means that we can't just take these pred y values and add or subtract from those, because we'd be doing that addition and subtraction on our real-world scale, when actually the standard error that we've got is on our link function scale, on our link scale. So we actually need to, instead of using the predict function to predict on the response scale as we just did, what I'm actually going to do is change this to link. Right. This means that we're going to predict values on the link scale. And I also want to add in the SE equals true argument. SE fit equals true. This is going to give us the standard error estimate. Kind of think of it as the standard deviation. And so if I predict this now, if I run this pred y object is now a bit more complicated. It's got several things in it, not just a sequence of values. It's got 100 different predicted values for our model fit, which is pred y $fit, as you can see here in the R console. But then it also, if you scroll down, it has pred y $se fit, right? These are the corresponding standard error estimates for each of those, right? And so what we want to do then, now that we've got these estimates on the link scale, is construct a new object, some sort of data frame that contains these values so that we can use them to predict kind of our model fit and confidence intervals, or to plot our model fit and confidence intervals. So what I do here is I make a data frame, and I say fit pred y $fit, right? So this is going to be a data frame with a column called fit that contains the pred y fit values that we just predicted. I also want the upper confidence interval. So I say, all right, give me upper and give me the pred y fit, but I want you to add to that the standard error times 1.96. Right, let's extend this a little bit so you can see, right? So the upper confidence interval here is going to be the pred y fit, right, our model fit. But for each point along that model fit, add 1.96 times the standard error, times the standard deviation. That's going to give me the upper confidence interval. And now that we've got the upper, the lower is going to be pretty much the same thing, except instead of adding, we're going to subtract the SE fit times 1.96. And so doing this will give me a data frame. Got some warning messages there. Yeah, now they're gone. It's just a mistake. Something must have been weird in the R console. If I run this, we see our data frame has 3 columns. Fit, upper, and lower, just as I said. And these are link scale values for the model fit and the confidence intervals, right? If I were to try to plot these, if I pulled up our nice plot, and now that I've got this fit on the link scale, right? Look at where that blue line plotted now. That's not on the real world scale because this is a logged line. So plotting that is not going to do us any good. We need to transform these. And so there's a couple ways to do it, right? You could just take this tpb.mod.fit object and transform it back onto the link scale. As such, I kind of like to embed the transformations in this data frame that I'm making, but in order to transform it back, you need to understand that there's not only a link function, which in our case is the log function, but each link function has an inverse link function, a function that will undo the transformation. The inverse function for a log is an exponent, right? Exponentiation is how you undo log transformation. And so, for example, the log of 0 that we had before, right? I don't know why it keeps giving me these error messages. The log of 0 is negative infinity, right? That is what allows us to transform our values of measurements that are bounded by 0 onto a Gaussian scale that goes to negative infinity. Now, what's the exponent of the log of 0? The exponent of negative infinity? 0, right? So log of 0 gets us to negative infinity. Exponentiating that gets us back to 0, right? Exponents undo that log transformation. And so what we could do is just take this TPB model fit object and exponentiate it. TPB model fit. If we did that, it would give us a new object where we exponentiated the 3 columns. That works. What I actually like to do is just put parentheses around these objects in that data frame to save time and put exponent in front of that. Now instead of the model fit, we're going to get the exponentiated model fit, which would be the same as in our predict function right here. Instead of saying type equals link, type equals response. When we say type equals response, what the predict function is doing is exponentiating our model fit anyway. So we're just doing it kind of manually here on the back end in order to calculate these confidence intervals. So if you put exp around all of these, make sure you put your parentheses in the right place. Exp, add one more to the end. Now if we make this data frame and we inspect it, those values that before were something like 4 point something, 1 point something, things like that, now they're back on the actual real world scale that we care about, right? We've got values in the 60s, 70s, and 80s. This is what we need in order to actually plot our real confidence intervals. And so let's go back up and run that plot. Let's do that. Let's get the AB line of our bad model, the regular linear model fit. And now what I want is to plot lines for the TPB.mod.fit, and we want the fit first of all, and we want to plot that as a function of new x curl, and do color equals blue. So that gives us our model fit from before, right? We could have done that just with the predict function, but as I said, the predict function struggles a little bit with the confidence intervals in this case, which is why we had to come up with this kind of workaround where we manually untransform it. And so instead I copied that over, but I want to change the $fit to $upper and $lower. And let's make, instead of line type 1, which is the default, let's make it line type 2 so that we can differentiate between the model fit and the confidence intervals. If I run these, look at those beautiful confidence intervals. All right. We can now see very clearly that our confidence interval, not only does our model fit stay above 0 in the GLM version, but our confidence interval stays above 0 too. If we were to just use the predict function and subtract the confidence interval like we did for the LM function, that confidence interval would have predicted negative values potentially. So this is why we had to do this workaround where we make this new object that is exponentiated versions of all of these. Right? If you forget that exponentiation is the inverse link function for log transformation, you can Google that. Right? Just Google when you're dealing with these types of models what the inverse link function would be so that you can transform it that way. And that will allow you to kind of better make confidence intervals and make your plots really well. Of course, you can also just copy paste the code from this tutorial here. Because that plot that we made is kind of an absurdly scaled plot, let's go back and just delete these xlim and ylim arguments from our plot. So we're just plotting the value itself, and now let's plot the model fit and the confidence intervals there. So this plot now is what we're really looking at with our data. This is a GLM, a log normal GLM, plotted on top of our measurement data as a function of the curl index. So you can see that there's a bit of a negative relationship here, and we've got this pretty horizontal line. I suspect that this is not going to be a very significant or perhaps powerful, even if it is significant, model fit, but we'll get to that next as we start interpreting the model summary.